Today we are going to discuss an introduction to polynomial equations and graphs. A polynomial equation in one variable is very similar to a quadratic equation in one variable. However, instead of stopping at an x squared term, we can go higher than x squared. So in general, a polynomial equation can be written in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 1x plus a sub 0 equals 0. Basically what happens is any type of equation in the form of something that looks like the following, like 3x to the fourth minus 5x cubed plus 2x squared minus 5x plus 3 equals 0, that is a polynomial equation. All the exponents on the variables are whole numbers and they're non-negative, which means they do not have negative exponents. They are not fractional exponents, anything like that. If they satisfy that requirement, then it is a polynomial equation. Now, the number k is said to be a 0 of the polynomial function if f of k is equal to 0. In other words, what we're looking at is we're looking at the fact that if you substitute in k, then everywhere you see an x, then you will get 0 for the entire equation. In other words, if you are dealing with real numbers, a 0 is the same thing as an x-intercept. However, you got to realize if it's a complex number, then it's no longer an x-intercept, we just call it a 0. We also call these things roots or solutions as well. So we could say that they are real roots or complex roots, or real solutions or complex solutions, depending on what type of solutions we find. So for example, for the following polynomial equations, we want to identify the degree and the leading coefficient, then check to see if x solves the equation. Now when they tell you to identify the degree and the leading coefficient, the degree of a polynomial equation is the number in which the x has the largest exponent on. Therefore, in this equation right here, 6x squared minus x cubed equals 12 plus 5x, that has degree 3 because that is the highest power you see on the x. Next, the leading coefficient is just the coefficient that's involved with that highest power of x. Therefore, if you notice, this is a negative x cubed, so the leading coefficient is actually just negative 1. Now when they ask you to check to see if x solves the equation, we want to see if when we substitute in a numerical value for x, in this case x equals 4, into the original equation, this one right here, if we get a true statement, we say that x solves the equation. It's actually a solution to the actual equation. So therefore, if they want you to check to see if x solves the equation, everywhere you see an x at, substitute in the numerical value, simplify, and see if you get a true statement. If you do, it does solve it. If you get a false statement, it does not solve it. So therefore, we can do the following. Everywhere we see an x at, we're going to put in 4. So 6 times 4 squared minus 4 cubed equals 12 plus 5 times 4. On the left-hand side, 6 times 4 squared gives us 96. Negative 4 cubed will give us negative 64, and that's equal to 12 plus 20. And if we simplify that even further, 96 minus 64 gives us 32, and 12 plus 20 also gives us 32. This is a true statement, therefore x equals 4 solves the equation. So if you look at the next example, we have x squared equals 2x minus 5. The highest power on the x is 2, therefore the degree of the equation is 2. And the leading coefficient is whatever is on that variable with the highest degree. And right here, the leading coefficient in front of the x squared is just considered to be a 1. So the leading coefficient is 1 here. Now they want you to find out if 1 plus 2i will solve the equation x squared minus 2x minus 5. Therefore, everywhere you see an x at, we're going to substitute in 1 plus 2i. So we have 1 plus 2i squared equals 2 times 1 plus 2i minus 5. But if we expand this part out, we end up getting 1 plus 4i plus 4i squared. That's equal to, distributing, we get 2 plus 4i minus 5. But 4i squared is really negative 4. Negative 4 plus 1 gives us negative 3. We still have a plus 4i, and that's equal to 2 minus 5 gives us negative 3 plus 4i. That's a true statement. They're both equal. Therefore, x equals 1 plus 2i solves the equation. Finally, we want to look at this one. We have x over 1 minus I equals 3x squared. Now in this case, the highest degree, or the highest power on the x is still a 2, so the degree is still 2. But in this case, the leading coefficient is not 1 anymore because now there's a 3 attached to the x squared. Therefore, the leading coefficient is 3. And now we want to see if x equals 0 solves the equation. So everywhere we see an x at, we put in 0. So 0 over 1 minus I equals 3 times 0 squared. But 0 divided by anything is still 0, and that's equal to 3 times 0 squared is 0. That's also true. Therefore, x equals 0 solves the equation. Now what we want to do is we want to discuss how to graph polynomials. To graph a polynomial function, we use the following steps. We first find the x and y intercepts of the function. We find the x-intercepts, recall, by setting y equal to 0, solving for x. We find the y-intercepts by setting the x equal to 0 and solving for y. We then use the x-intercepts to find the intervals on which the graph of f is above the x-axis and the intervals on which the graph of f are below the x-axis. We will do this by splitting up the real number line. From negative infinity to infinity, we will split up that whole interval into subintervals using the x-intercepts found in step 1. Once we do that, we will then choose test points within each of those subintervals and determine if the answer is positive or negative when we substitute those test intervals or test numbers back into the equation. If it's positive, that means within the interval, the graph will be above the x-axis. If it's negative within that subinterval, then that means that the graph will be below the x-axis within that subinterval. And that is step number 3. This is best done by example. It says, sketch the graphs of the following polynomial functions, paying particular attention to the x-intercepts, the y-intercept, and the behavior as x goes to infinity and negative infinity. We will talk about this part here in a few moments. Notice, if you look at part A, it says f of x equals negative x times 2x plus 1 times x minus 2. With that being the case then, the very first thing we want to do is we want to find the x-intercepts. And we do that by setting y equal to 0. Or in other words, that's setting f of x equal to 0. So therefore, we're going to have 0 equals negative x times 2x plus 1 times x minus 2. When we do that, notice that the right-hand side is already factored out. So we don't have to factor this at all to find the x-intercepts. We just have to set each factor equal to 0. So we have negative x equals 0, 2x plus 1 equals 0, and x minus 2 equals 0. Therefore, x is equal to 0, x is equal to negative 1 over 2, and x is equal to 2. So the x-intercepts are 0, 0, negative 1/2, 0, and 2, 0. Next, we find the y-intercept by setting x equal to 0. But that means everywhere we see an x at, we put in 0, so f of 0 equals negative 0 times 2 times 0 plus 1 times 0 minus 2. That's going to give us 0 times 1 times negative 2. That still gives us 0. So the y-intercept is 0, 0. Now, step 2 of this process tells us to use the x-intercepts to split up the real number line into subintervals. So we always start at negative infinity. So here we'll start at negative infinity, and we work our way up until we hit the first x-intercept. Now, between the x-intercept of 0, negative 1, and 2, the first one we come across when we start from negative infinity is negative 1/2. So I will end at negative 1/2, and we always use parentheses in this case. We never use brackets. We then pick up where negative 1/2 left off, and we go on until we hit the next x-intercept. But the next x-intercept is 0. We then pick up from 0, and we go on to the next x-intercept, and that's 2. But then notice we have run out of x-intercepts, therefore this last interval is going to go all the way up to infinity. We are then going to choose a test point within each one of these intervals. And so you always choose one of the easiest test points to use. Therefore, I'm going to choose -1 here. I'm going to choose -1/4. I'm going to choose 1, and I'm going to choose 3. Notice I chose the easiest numbers within each interval. And what I need to do is I need to substitute in each one of these test points into the function. So I'm going to choose, so for example, in the first column here, I'm going to put in -1 everywhere I see an x at inside the function f and see what we get. So we evaluate the function at every test point. So this is going to be f of -1 is equal to minus a -1 times 2 times -1 plus 1 times -1 minus 2. And if you do that, you should get +3. And if you substitute in -1/4 everywhere you see an x at here, then you're going to get a -21/32. Substituting in f of 1, we get 3, and substituting f of 3, we get -21. Based on the sign of these answers, what we just got, we can then determine within these intervals if the graph is going to lie above the x-axis or below the x-axis. Since this answer of 3 was positive, we know that the whole graph is going to be above the x-axis here. It's going to be below the x-axis between -1 and 0. It's going to be above the x-axis between 0 and 2, and it's going to be below the x-axis from 2 to infinity. Therefore, what we have is the following. Graph everything we know. Now the first points we found were the x and y intercepts. So one of the x-intercepts was 0, 0, and incidentally that was the y-intercept as well. This is -1 here. This is going to be -1/2, 0. And then 1, 2, this is going to be 2, 0. So we always plot the x-intercepts and the y-intercepts first. Then all these test points and answers to the functions of these test points are all ordered pairs as well. So therefore, let's go ahead and plot those also. So we have -1, 3, -1/4, -21/32, so that's almost right here. We have 1, 3, and then finally we have 3, -1, or I'm sorry, -21. So that's way down here somewhere. So then we connect the dots. Notice that we've determined between -infinity and -1/2 that everything lies above the x-axis. Therefore, from -1/2 all the way to -infinity, it's going to have to increase like this. Because if it ever dipped down, it can never go below the x-axis. Therefore, we connect the dots and extend the line up that way. We then realize that the graph then touches -21/32, but then it has to curve back up because it has to cross 0, 0. So then we know it has to come back up this way. But then we know next it has to cross the x-axis again at 2, 0. But then once it gets 2 to beyond, it must always stay below the x-axis. So therefore, it must look like this. So as you can see, as x goes to -infinity, the whole function also goes to infinity. We also know that as x goes to +infinity, the whole function goes to -infinity. So that is what we call in behavior. And so we've graphed the function for this first scenario here. Next, we have the following function, x to the 4th minus 1, or g of x equals x to the 4th minus 1. Now the first thing we always want to do is try to factor this out as much as we can. We should note that this is a difference of two squares, therefore we can split this up into x squared minus 1 times x squared plus 1. But x squared minus 1 is also a difference of two squares, so this is x minus 1 times x plus 1 times x squared plus 1. Therefore, what we do is we first find the x-intercepts, and we do that by setting the function equal to 0. Therefore, what we're going to have is we're going to have 0 equals x minus 1 times x plus 1 times x squared plus 1. Well, since it's already factored, since we did that up here, all we have to do is we have to set each factor equal to 0. So x minus 1 equals 0, x plus 1 equals 0, and x squared plus 1 equals 0. Now this one right here is not going to give us real solutions or zeros. This is a complex solution, but that's not going to help us when graphing these graphs. Therefore, this is not real, but this is going to give us an x is equal to 1 and an x equal to negative 1. Therefore, our x-intercepts are 1, 0 and negative 1, 0. The y-intercept is when you set x equal to 0. So therefore, if you take f of 0 equals 0 to the 4th minus 1, that gives us negative 1. So therefore, the y-intercept is 0, negative 1. Now we choose intervals. Therefore, we always start at negative infinity and work our way up. The very first x-intercept we come across is negative 1. Therefore, we go from negative infinity to negative 1, negative 1 to the next x-intercept of 1, then we go from 1 all the way up to infinity because we ran out of x-intercepts. We then choose a test point between each one. Well, if we choose a test point though, the easiest point between negative 1 and negative infinity is negative 2. We have 0 here and we have 2 here. And so now we evaluate the function at each of those test points. Therefore, everywhere we see a x at, we're going to put in negative 2. So g of negative 2 is actually going to give us 15. G of 0 is going to give us negative 1. And finally, we have here g of 2, that is going to give us 15. Therefore, what we know is the following. Since we know that this thing is positive right here, we know that the whole graph, when we graph it, is going to be above the x-axis between negative infinity and negative 1. Between negative 1 and 1, since the g of 0 was negative 1, that is going to be below the x-axis. And then this is going to be above the x-axis. Therefore, we can now graph the polynomial equation. First, plot all x-intercepts and y-intercepts. Our two x-intercepts were 1, 0 and negative 1, 0. We also have a y-intercept of 0, negative 1, so that's 0, negative 1 here. We then plot all the other points we know. From the test points and the g evaluated at the test points, we know that we have negative 2, 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's going to be right here. We also have 2, 15. We have right here. Now, everywhere from negative 1 to negative infinity, we're going to be above the x-axis. So when we go from here up, it has to cross through this point, but it has to keep increasing. The reason for that is because if it ever decreases, it can never cross the x-axis because there's no other x-intercepts, and it would dip below the x-axis, and we know it's not true based on our test points. But between negative 1 and 1, we know the graph should be below the x-axis, so therefore it should go through this point and come back up because it has to cross this x-axis here. And then finally, it must keep continuing on that way. And again, it can never cross the x-axis again because we know that there are no other x-intercepts. And we also know from the test points that from 1 to infinity, it's always above the x-axis. Therefore, we have graphed this equation here. Finally, we have h of x equals x squared plus 2x minus 3. Now, you should verify for yourself that this factors into x plus 3 times x minus 1. And that this is going to give us x. The x-intercept is when we set the whole function equal to 0. So this is going to be 0 equals x plus 3 times x minus 1. But we can set each factor equal to 0. Therefore, x equals negative 3 and x equals 1. So the x-intercepts are negative 3, 0 and 1, 0 respectively. We also know that for the y-intercept, we set x equal to 0. Therefore, we would take h of 0 equals 0 plus 3 times 0 minus 1, but that gives us negative 3. So our y-intercept is 0, negative 3. We then do some intervals. From negative infinity, we come across our very first intercept, and that's negative 3. We then go from negative 3 to 1, and then 1 to infinity. We choose some test points between each one of those. So therefore, I'm going to choose a negative 4 here, a negative 1 here, and a 2 right here. We then find h of our test point, meaning everywhere we see a x at, we put in whatever the test points we chose. So h of negative 4 is going to give us 5. H of negative 1 is going to give us negative 4. And h of 2 is going to give us 5. Therefore, this is going to be above the x-axis between the intervals of negative infinity and negative 3. This is going to be below the x-axis. And this is going to be above the x-axis. So therefore, what we can do is we can finally graph our function. And if we do that, we plot all the x and y-intercepts first. So negative 3, 0 would be right here. 1, 0 would be right here. And 0, negative 3 would be right here. We then have the ordered pairs that we found when we did the test points and substituted in what the test points were in the function. So we have negative 4, 5. We also have 2, 5 here. And we have negative 1, negative 4. Therefore, what we know from negative infinity, so from here to here, from negative infinity to negative 3, we know it always has to be above the x-axis, so it must extend up that way. We then know it has to come down, come across this section right here, has to come back up, go through this point, and then it has to come to that x-intercept there. And we know from negative 3 to 1, it must always be below the x-axis, so we know we've drawn that correctly. But then as soon as it crosses 1, it is always above the x-axis, and we know it has to go through this point, therefore it goes up like that. We have then graphed this polynomial function. The last thing we want to talk about is how to solve polynomial inequalities. To solve a polynomial inequality, we follow these steps. We write the inequality so that a polynomial expression f is on the left side and 0 is on the right side. So basically, we get 0 on the right side, we get everything else on the left-hand side, so we use the addition property of equality if necessary. We then determine the real zeros, or the x-intercepts of the graph of f. We then use the zeros found in step 2 to divide the real number line into intervals, just like we did above. And then we select a test point within each interval, evaluate f, and if it's positive, we know that the graph is going to be above the x-axis, which means it's going to be greater than 0. If it's negative, we know it's going to be below the x-axis, or in other words, it's going to be less than 0. And then we choose whichever ones are appropriate for the inequality that we have. This is, again, best done through example. So, part A says to solve the inequality 2x squared minus 3x is greater than 9. So So the first thing we want to do is get 0 by itself on the right-hand side. So therefore, I'm going to subtract 9 on both sides. So this is going to be 2x squared minus 3x minus 9 is greater than 0. So this is step 1. Step 2 is to find the x-intercepts by setting the function equal to 0. Therefore, what we're going to have is we're going to have 2x squared minus 3x minus 9 equals 0. But you should note that 2x squared minus 3x minus 9 will factor into 2x plus 3 times x minus 3, and that's still set equal to 0. Setting each of these factors equal to 0, we get that x equals negative 3 halves and x equals 3. Therefore, the third thing that we're going to do is we're going to choose some intervals. Well, we do the same thing as we did above. We go from negative infinity all the way up to the first x-intercept we come across, which is negative 3 halves. We pick up from negative 3 halves to come to the next x-intercept, which is 3. Then we keep up with that x-intercept and we go on to infinity because there's no other x-intercepts. We then choose test points like usual, just like above. Therefore, I'm going to choose negative 2, 0, and 4. And we evaluate the function at each of these test points. So therefore, we have f of negative 2. And if we substitute in everywhere we're seeing x at in a negative 2, we get 5. We have f of 0 gives us negative 9, and f of 4 gives us 11. Now in this case, we're not interested in graphing the graph, or the equation, or inequality. We're just interested in finding the solution to the inequality in interval notation. Therefore, since this test point, when we evaluated the function at that test point of negative 2 was positive, we know that f of x is above the x-axis in this interval, which means it's greater than 0 at this case. Now, since it's negative, all values of f of x is less than 0 in this case because the value was negative in our test point. And then all values of f of x are greater than 0 because when we evaluated the function at the test point of 4, it was positive. Therefore, notice our original inequality was greater than. So therefore, we want to find all intervals in which our test points gave us when we evaluated the function greater than 0, which was here and here. Therefore, the solution for our x's are from negative infinity to negative 3 halves, union 3 to infinity. Now again, we don't use brackets here because if we put in negative 3 halves or 3 inside the inequality, we'll get equal to 0, but this inequality was strict, therefore we don't use brackets. Therefore, this is the solution to this inequality. Next, we have x to the fourth minus 2x squared is less than negative x cubed. So in this case here, we have to first get the right-hand side 0. Therefore, what we're going to do is we're going to add x cubed to both sides. So we're going to get x to the fourth plus x cubed minus 2x squared is less than 0. So with this being the case, what we have is we can do the following. First, we can factor out, well, number 2 is we do the following. We find all x-intercepts. We do that by setting the function equal to 0. Therefore, we're going to have x to the fourth plus x cubed minus x squared is equal to 0. But first, we can factor out an x squared. That's going to leave us with x squared plus x minus 2, and that's still set equal to 0. You should realize that x squared plus x minus 2 will factor. And that factors into x plus 2 times x minus 1, and that's still set equal to 0. Therefore, we can set each factor equal to 0 using the zero factor property. And so we get x equals 0, x equals negative 2, and x equals 1 as our x-intercepts. Therefore, we create our intervals from negative infinity the first x-intercept we come across is -2. We then go from -2 to 0, 0 to 1, then 1 to infinity. Again, we break up the whole real number line with our x-intercepts. We then choose some test points between these intervals. So I'm going to choose -4. I'm sorry, -3 would be easier in this case. A -1, a 1/2, and a 2. So then we evaluate the function at each of these test points. So therefore, we're going to find out what f of -3 is. But everywhere we see an x at, if we put in -3 inside of this equation right here, we're going to get 36. Therefore, the function f of x is going to be greater than 0 for all values between -50 and -2. Because when you evaluated the function at that test point of -3, we got a positive 36. Then we evaluate f at -1. Everywhere you put a -1 at inside of x, you will get -2 after you solve. But that means that the whole function is going to be less than 0 because that 2 was negative. Then we're going to put in f of 1/2, and if we solve for that, that's going to give us -5/16. But that means that f of x is still going to be less than 0 at that case. Then finally, if we put in f of 2, that's going to give us +16. Therefore, the function f of x is going to be greater than 0 in that case, because we got a positive number. Therefore, look at the original inequality, and we want everything less than 0. Therefore, circle everything that's less than 0 at the very bottom row here. This is less than 0, and this is less than 0. But the inequality was strict, which means there was not or equal to, so we cannot include the x-intercepts. Therefore, the solution set is -2 to 0, union 0 to 1. We cannot include -2, 0, or 1 because all those would make the function equal to 0, but we have a strict inequality of less than, not less than or equal to. So this is the answer here. Finally, what we have is we have this inequality. Notice that they were good to us this time, and they gave this to us in factored form first, so we don't have to factor it out. But we still have to find the x-intercepts. So 1, we already see that it's the right-hand side is 0, so therefore we don't have to do any manipulation to this. Therefore, the second step is to find the x-intercepts, and we do that by setting the function equal to 0. So we'll have x plus 3 times x plus 1 times x minus 2 is equal to 0. So that means x is equal to -3, x is equal to -1, and x is equal to 2. Therefore, we can split up the real number line into subintervals. So from -infinity, the first x-intercept we come across is -3. We then go from -3 to -1, then -1 to 2, and then 2 to infinity. So therefore, we choose some test points. Here, the best points to choose is -4, -2, 0, and 3. And then we evaluate the function at each of these test points here. So let's find out what f of -4 is. But f of -4, everywhere you see an x at, you put in -4, you're going to get -18, which means that the function is actually less than 0 here. If you put in -2 everywhere you see an x at, you're going to get +4. But that means the whole function is greater than 0, or above the x-axis here. If you put in 0 everywhere you see an x at, you're going to get in -6, which means the function is actually less than 0. Then finally, if you put in f of 3, that is going to equal 24, and therefore the function then for that whole interval is greater than 0. Now, since our inequality was now greater than or equal to 0, we don't want to include anything where the function was less than 0. Therefore, we have to include this one here because it was greater than 0, and we have to include this one here because it was greater than 0. However, notice now it's greater than or equal to, which means that we can do the following. We don't just include this, -3 to -1 union 2 to infinity. We also include the -3, -1, and the 2. The reason for that is because we can have or equal to 0, and those are x-intercepts, which means it is equal to 0 if you substitute in those values. Therefore, in this case, when it comes to -3, -1, and 2, we use brackets. So this is the answer here. This concludes the section on Introduction to Polynomial Equations and Graphs.